Hello everyone, my name is Qiu Yiqi. Today I will present this paper. The title is Formation of Halogen-bearing Species, Irradiation of methyl fluoride in carbon monoxide ice with UV light and electrons. This paper was published at the Astrophysical Journal in 2019. This is my outline of this paper. I will explain why this paper is interesting in halogen species formation. After that, I will introduce experimental methods, including instrument sample preparation, photolysis by synchrotron radiation and UV light, radiolysis by electron gun. After that is result and discussion. Finally is conclusions. Most of space elements, including hydrogen, carbon, oxygen, nitrogen atoms, it's rare to see the halogen species or halogen atom. However, halogen hydride have been identified in recent years, but it's very simple halogen hydride, such as hydrogen fluoride or hydrogen chloride. This is why the author wanted to know more about the halogen species formation, because it's rare. In order to simulate astrochemistry, it is important to investigate the mechanism of halogen species formation. In ultra space, cell-grain is abundant, so cell-grain may play an important role in ultra space. In this paper, using methyl fluoride and carbon monoxide ice to study. This slide I will introduce what is synchrotron radiation. Synchrotron radiation is generated when a charged particle traveling at the nearly speed of light. For example, charged particle is electrons. In National Synchrotron Radiation Research Center, which is called NSRC, in TLS, first they will inject electron by electron gun in booster ring and through the transport line to storage ring, linking to the bin line to do experiments. This paper used third-generation synchrotron radiation, which is applied insert device, such as undulator or wiggler to increase the energy of synchrotron radiation. This plot is wiggler, this plot is undulator. When electron beams fly at the nearly speed of light and deflected by magnetic field, this magnetic field is composed of NS, and they will emit electromagnetic wave along the tangential direction. This is generation of synchrotron radiation. According to the photon kinetic energy and intensity, it can choose what kinds of insertion device to be applied. Synchrotron radiation have a lot of advantages, such as higher intensity, higher flux, tunable energy source. Experimental including 4 parts. First is instrument. Second is sample preparation. Prepare a molar ratio in 1/250 methyl fluoride and carbon monoxide ice. Third part is photolysis by synchrotron radiation and UV light. The fourth part is radiolysis by electron gun. This paper used synchrotron radiation to be one of light sources. This picture is optical layout of Taiwan light source DO3A1 beam light in NSRC. It is called dragon-type beam light with horizontal focusing mirror and vertical focusing mirror, move about distance of mirror and slit, which can eliminate aberration. At the end, it will refocusing again. You can switch the optical components with proper choice according to different end station. Dragon-type beam light not only can decrease the error of the light, but also increasing the stability of light source. This slide will introduce experimental instrument. Use a closed-cycle helium refrigerate to cool the target, which is gaseous sample. A nickel copper plate serves as a cold substrate, and pumping the air less than 10 to the power of -8 tool. An electron gun will to bombard the ice sample to compare with the photolysis method. The electron volt will set 300 or 3000 electron volt. FTIR will operate to measure absorption spectra with 400 scans, and its resolution is 0.5 wave number. Its splitter is KBR. Temperature controller with a hybrid silicon diode. Its accuracy is positive or negative 0.1 Kelvin. In order to prepare a gaseous mixture at a molar ratio 1/250, this paper uses partial pressure method. This is schematic of partial pressure method. For example, open one of gaseous cylinder. Methyl fluoride first and open its valve to measure its pressure. For example, 1 2, and the gas will pass the tube to sample cell, and close the gas supply and open the seal again to measure it at 250 2, and you can get a 1/250 gaseous mixture. Next day, the gaseous sample will directly introduced into a chamber. A gaseous sample will deposit on the cold target over a 2-hour period, and its flow rate will set 1 millimolar per hour. Thickness of ice is 10 micrometer. After that, the author tests the temperature effect to the gaseous sample. Gaseous sample will deposit at different temperature. The black line is 10 Kelvin, the red line is 20 Kelvin, and the blue line is 30 Kelvin. You can see that the absorption spectra of 10 Kelvin and 20 Kelvin are similar, but after 30 Kelvin, the CO started to sublimation, so the methyl fluoride may cluster together or it will diffuse, so its band position bandwidth is different from 10 and 20 Kelvin. Let's see the most intense absorption is μ3, which is CF stretching. When temperature raises, CO will interact with CF bond, resulting a strong disturb to μ3. So as temperature increases, the IR band will become broadening. This is assignment of this spectrum. So photolysis and radiolysis experiments will operate and take Kelvin. This reference paper used two different light sources to photolysis carbon monoxide ice. The first light source is UV light generated from microwave discharge hydrogen flow lamp. It's a common tool in astrochemistry lab. After photolysis CO ice, there are some photo products formation. But the second light source is synchrotron radiation at 121.6 nanometer. After the photolysis, there is no photoproducts formation. It can be explained as synchrotron radiation will penetrate CO ice in 121.6 nanometer. So different light sources may have important effect to ice sample. In this paper, two kinds of light sources were used. First is Lyman alpha light from synchrotron radiation. Second is UV light generated from D2 lamp. Both of light sources are dosage of 10 to the power of 7 photons. So the irradiation time will differ. What is Lyman alpha? According to this Lyman series formula, Lyman alpha is when n equals 2. So after calculation, the Lyman alpha light will be 121.6 nanometer. The figure 2 is absorption spectra of photolysis ice sample. The red line is synchrotron radiation. The black line is UV light. So you can see that CO2 absorption is slightly different depending on its shape, its bandwidth. Because the formation of CO2 is uncertain. So assume that different bands originated from different light sources. This is the assignment of this spectrum. After two kinds of photolysis experiment, it can compare the difference. First, consider that CO ice doesn't absorb Lyman alpha light in 121.6 nanometer. So the product from Lyman alpha is dissociation from methyl fluoride, while UV light is more wide range from 150 to 160 nanometer. It can excite both of methyl fluoride and the CO. But the fragments are very rare because UV light cannot penetrate ice very deep, so only the upper layer can be photolyzed. Moreover, it needs to dissociation continuously to form product according to this reaction. So the mechanism is limited. So next experimental part will use electron gun to bombard the sample. Because dissociation of CO requires electron volt 11.1 electron volt. This falls outside of photolysis range. Electron gun can generate more high energy level than it. Using electron gun is benefits such as readily break molecular penetrate sample more deep, give some probability to generate photoproduct. So in this paper, use 300 and 3000 electron volt to irradiate the ice sample. The parameter of electron gun kinetic energy set 300 or 3000 electron volt, and flux be so much electron per second. The target is 2 multiple 2 squared. This is the IR spectrum of radiolysis with electrons. The red line is 3000 electron volt and the black line is 300 electron volt. So let's compare the absorption spectra of photolysis and radiolysis. You can see that the photolysis and radiolysis are completely different. They are much more bent. So using electron gun can generate more product. It confirms that electron gun is more efficiency. This is assignment of the absorption spectra figure 3. After bombarded by electron gun, the IR spectrum becomes more complex. It forms more radical cation products compared to photolysis as compound. For example, protonated carbon dioxide. It means that more fragment, more radical, so more the halogen species formation. Let's see the mesio-radical absorption. It increased, so it means that F18 increased. The halogen species formation increased. The most strong band in this spectra is FCO, because its enthalpy favored by calculated density function theory. Let's compare the photolysis and radiolysis. In photolysis experiment, the probability for producing carbon-oxygen atom is really low, and it cannot penetrate CO ice very deep. And CO diffuse will limit photoproducts formation. The CO dissociation energy is 111.8 nanometer. It's out of range. But radiolysis by electron gun, its probability increase and it can penetrate the ice to more deep. So the photoproduct increase. Here is my conclusions. Temperature is impact factor to halogen species. Different light sources may lead to different mechanisms. Electron gun is more efficiency to simulate astrophysical environment, causing the radical recombined with ion reaction. Thanks for your listening. This is my report.